Okay, let's record. Good morning. Let's continue our discussion on support vector machine. Okay, let me share my screen. Okay, so we are saying that support vector machine is used to classify uh, data. So in this case, we are showing two sets of some sort of objects. Yeah. So we want to classify those objects into two. One is the circle, blue circles, and the other one is the red triangle. So there are many ways of separating them, linearly separating them. Okay. On the top, we say that we can linearly separate these two distinct objects by a vertical line on this side. We say that they can be separated by this slanted line. So now we are saying that there is a better way of separating them. Okay. So before we go there, we say that there are cases where they are not linearly separable. That means we cannot draw a line to separate the two types of objects. In this case here, well, we can actually, but there is some sacrifice of this point that you cannot separate. So for example, if we draw a line here, so that is separated, but there is this object here that is not correctly classified, but it's fine. And in some cases we make sacrifices. It's fine as long as the rest of them are correctly classified. But here in this case here, there's no way we can classify them linearly. So there's something like we classify them non-linearly. Okay. In this case, around those objects. Okay, around the blue lines. So how do we do this? Okay. Let's just discuss how things are classified. Okay. So in support vector machine, we use a linear function. Okay. This linear function, okay, creates, okay, this is an equation of a line. Okay. So let's just consider, because I didn't write it explicitly before. So we say that your W, your vector W, consists of, in this case, let's consider the planar case where you have W1 and W2. Okay, so now, okay, how come your cameras are not, I don't see your cameras? Porapileng, you still don't have a camera.
Yes, sir. My camera doesn't work.
Your camera doesn't work. Can you just go to one of your friends next time so we can see you while we are having a class? Jepang, Tutate.
Yes, sir.
Okay. So now that is your W. We say it's two-dimensional, and your X also, in this case, is two-dimensional planar. So instead of instead of using Y, we want to use X1 and X2. So X1 and X2. So there are two components. Okay. And in your B here, B is a scalar. It's not a vector. You can see this is slanted and these are bold. Okay. So this is X1 and that X2. Okay. So for every point here, this point has some value X1, X2. Okay. X1, X2, I. Okay. Okay, then maybe here another value of X1, X2. Let's say J, yeah. So that means here this is equal to Xj, that vector Xj. And in this case here, this is your vector. Okay. And then you can plot them in that plane. Okay. Is there a question there? Of course, we don't have any question on that one. So that means here, we can write this one as this because that's a vector. So that means this is W1, W2. X1, X2. plus b. Okay, so in essence we have w1 1 plus w plus b. Okay, where b is the bias. Okay, now this value f of x will tell us what is the classification. So now we are saying that if the points are here, when you evaluate this value f of x, it will be less than 0. Okay, if your point is somewhere here, you evaluate this w1 x1 plus w2 x2. That means multiply the weights multiplied by the location of that point in the plane plus the bias will result into less than 0 scalar value. Okay, it could be, for example, maybe it could be minus 0.2, yeah, or it could be minus 10, yeah, or it could be minus 200. Okay, so normally your value becomes bigger and bigger as you go away from the boundary. Okay, so when you're in the boundary, your value of f of x, if you have an x here, if you have a point here, the value when you evaluate this wx plus b for that x that is there is equal to 0. Okay. Mopati, can you just turn off your microphone for now because there are.
Turn it off.
Yeah. Okay, yes. Okay, that's better. Okay, now, so I want you to understand that our W value and our B value does not change. They don't change. Okay, they are constant throughout all these classifications. All we need to do is plug in the X, and then it will give you some value of f of x that will be less than 0 when you are on this side of the classification of that line or that hyperplane, and greater than 0 when you are in that side of the hyperplane. Okay, when you are on that line or the hyperplane, okay, the line, if you look at it from the top, okay, then the value of f of x when you evaluate is equal to 0. So again, the value of w and b are all the same for all x's. All you need to do is evaluate the x, the point that is on these data sets, and on these data sets or data, this group of data or a group of say objects. Then here you can say that for all objects here, the evaluation of f of x is equal to 0, less than or equal to 0. And on this side, the evaluation of f of x is greater than or equal to 0. You will be 0 on when you're on the line itself. Okay, so the problem here actually is that we want to know what is the value of w. We will be looking for the value of w as well as the value of b, so that we can come out with the right value of classification. That means for all points in this area, in this region, you will have an f of x is equal to 0. And for all points in this region, you'll have f of x greater than 0. So that's the thing. We need to find what is the value of w, and we need to find what is the value of b. Okay? Is that clear? Okay, I hope that's clear. I think that's clear. Huh? I practiced that one so that you will find it clear. So now let's start with the perceptron classifier. Perceptron classifier is the simplest version of support vector machine. So it only considers the linear problem or the linear classification. In this case here, we have the same equation, okay, f of x, I, where your I is okay, your data, okay, your data value. So let's just say you have I, okay, and you have your xi. Xi can be x1, x2, and your yi, okay, your yi is the classification here, -1 or plus 1, okay? So now, we say, for example, for the ith data, then maybe you have x1, x2. So we say here x1, xi of x1, x2. So maybe you have 1 and 0.5. And then your classification is, remember that your x1 here bigger, x1, and then x2 here. So maybe let's just say when your x, maybe this is 1. Let's just assume that's 1 and that's 0. Okay. When your x is great, your x1 is 1, then your classification is 0 because you're right on that line. Okay. So next, if your x1 is 1.5, it doesn't matter what your y is. Okay, it should be 1, greater than 1. Okay, I mean greater 1 instead in terms of classification. Or, okay, because this one is exact, we have to put it 0. Okay, for those that are greater than or 0 in this side, we make it -1 or +1. So that's +1. On this side here, we say 0.5. That means it's somewhere here. Okay, it's a circle. Here is a triangle. Okay, so it doesn't matter what your y is. It could be 10. Then here it's -1. Okay, and so on. Okay, we can have as many, maybe 100 data points. Or let's just say 10, so that it's 10. Okay, so you have 10 data points, and these are how your things, your data is presented. Okay, 10 points, and then you classify, you put the coordinates on the plane, and then you classify them accordingly. Okay, so now we are given that one. Okay, so now we want to know what will be the value of the W. So I, in this case, I goes from what? Moses. I goes from Moses.
Get the question.
I goes from, in this case, I goes from this, we are given this data. So we say that I goes from
1 to 10.
Okay, 1 to 10, because you have 10 data points. So very good. Yeah? So very good guess. You're lucky this time, Moses. Okay. Okay. So now, so out of these 10 data points, xi, we want to know what is the value of w and b. That will give us this kind of classification. Okay. That will give us a correct classification, maybe greater than or equal to 0 in the f of x. But eventually, if greater than 0, that means that it's a 1 classification. If less than 0, that's a -1 classification. So now, in the Perceptron classifier, so 10 is equal to 10. Okay, so separating hyperplane, we know this already, that it is a line. Okay, it's a line, but it can be a hyperplane, that means it's a plane. Okay, separating the two, it's like a wall between the two in the plane. A wall, if you see from the top, it is a line. Okay, so that wall is a hyperplane, we are saying. So now we write the classifier like this. So now instead of, normally we're saying that W goes from, we say W is from, consists of W1, W2. Okay, and your X consists of X1, X2. Now we want to put them in a more compact form. So the more compact form is that we include the W0. The W0 is the B now. Yeah. So the W0 is the B, and we include the X part of the X. Now XI has a 1. So now your W, okay, well, this is your W that is tilde and WX that is tilde. So now the final W will be, you have W1, W2, okay, and W0, okay, or yeah, or we can rewrite it in the final form. W0, W1, W2, and your X. So that takes care of the bias. Okay. So in this case, 1, okay, and X1, X2. Okay. Now all you need to do is put f of x as this multiplication. Okay. The bias is inside already. So all we need to consider is W transpose times Xi. So now, when we consider this vector multiplication, we need to know how to update the W's. So W's, the W1 and W2 is the original value of W here, and W0 is the bias. Okay. So what we really need to know is that what are the values of all the weights so that we can classify them correctly. So how do we do this? Well, we say that we want to use this kind of iterative classification where you initialize your W, okay, multiplied, you add with some learning rate multiplied by the sign of the value of Xi. That means that in this case, if it's greater than or equal to 0, and then that's a 1, or it's a positive 1. If it's less than 0, it's a minus 1. Okay, so now that's the sign. Okay, so there are two classifications multiplied by your input Xi. So now, if your Xi is misclassified, then you update. This is the one. It says if there's a misclassification, then you correct your W by some learning rate multiplied by the line of the function of Xi multiplied by Xi. Okay, until all the data is classified. Okay, this is the way Perceptron is doing. So if all the data are all classified, correctly classified, it's like an if else. Yeah, if, okay, for example, misclassification, how do we say that it is misclassified? How do we say that it is misclassified? When your f of x I multiplied by your yi is less than 0. Okay, why is that? Then there's a misclassification. Then you update your W. W is equal to W plus this step size. You understand that? Why is it that f of xi times xi less than 0 is considered to be a misclassification? Bright, I have not seen you. I have not called you for a long time.
What was the question again?
I guess the student, if the student is asking like that, it means they're not listening, right? It could be for sure. Yeah. Are you watching something in your phone? Looks like you are messaging someone. Can you bring up your phone like that and show? I mean, I don't need to read the message, but there's a phone down there on your table, right? Show me. Show
Yeah,
me. There's a phone. Yeah. There, you were looking at it. Okay. The question is, we are saying that we will apply this update of the W. We want to apply the update of the W when XI is misclassified. Okay, so that means is everything. If you go through all you check the classification of f of xi and your xi is in here, and your f of xi is less than 0, then of everyone in this direction is less than 0, and you check your xi in this, this location is greater than 0, the classification, then you don't need to correct the W's. Your W's are okay. But if there's a misclassification, then you need to update your W by some step size multiplied by the sign times xi. Okay? It means somehow we want to correct it, hoping eventually that as you go through all the iterations, it will become corrected, so that now you can classify them accordingly. Okay? Then the question is, why do we say that this one, f of xi times yi, if it's less than 0, it is a misclassification? Remember that in our computation here, we are saying that for all x's, for all xi, in this region, f of xi is less than 0. Okay, do you see what I'm writing on the board? Is it clear to you or no? Yeah. Okay. And then in this region here, f of xi is greater than 0. Okay, so in this region here, f of xi is greater than 0. They're classified as positive 1 in terms of our yi. In this region here, in terms of your yi, they're classified as -1. Sorry. Okay, so why do we say that misclassification is like this? It's because it's now looking right into your face. Masa. Why do you think? Misclassification is, they're considered to be a misclassification if your function f of xi multiplied by the yi is less than 0. From here, just look at from here.
I think that it cannot be, the classification cannot be 0. It's greater than 0 or less than 0, not 0 on the dot.
0 on the dot if the x is on the line. That's possible. But let's assume that everything is not, all the dots are not stepping on the line. So yes, let's consider a non-zero one. But we are saying that if it's less than this multiplication, f of xi times yi is less than 0.
So can I?
Yes.
I think if they're correctly classified, then you have f of xi and yi having the same sign. And if they have the same sign, when you multiply them, then you have a positive number. But if they have different signs, then you have a negative number.
Okay, and so if you have different signs, that means that
so if
they have different signs, it means that
it's going to give a number which is less than 0.
Yes, that means that
they're misclassified.
Yes, they are misclassified if the signs are different. Because you can see here, your f of x evaluation for all points located in this region, it's less than 0. That's what we are setting. Okay, I'm not saying that's what we are setting here. Okay, all the things, all the points in this region, your f of x is less than 0. All the points in that region, your f of x is greater than 0. But then all the points here are minus. These are negative, -1, and these are +1. The same, this is the classification of the yi. Okay, so that's why we have +1 and -1. This is an exception because this one is stepping on the line. So anyway, let's assume just for this argument that all points are not stepping on the line. And so now, so in this case, your f of x evaluates for any point. If you evaluate your f of x, that means you evaluate w, t, xi plus b for all the points in this region, then that value will always be less than 0. Okay? Thus, their classification is -1. Your yi, for example, your xi here is less than 0. So in this case here, your yi is equal to -1. Okay? So it could be xi plus 1. Okay, xi plus 1. Then again, we take xi plus 1 here, then it will be less than 0 again. And then your yi plus 1 will be also -1 if they are correctly classified. That means they belong there. That means you have a blue dot here. Everything is a blue dot. But then if you have a blue dot somewhere here, once you have a blue dot here, that means that classification, that blue dot, okay, because it is in this region. So the evaluation of that blue dot is greater than 0. But because it is a blue dot, it's classified as -1. Okay, greater than 0, f of x greater than 0, that means a positive number multiplied by a -1 because it's a blue dot. A blue dot corresponds to a -1. So the multiplication is less than 0. Okay, here. But on the other hand, if you have a red triangle in this region, a red triangle is considered to be +1 classification. So that +1 classification, and then if you evaluate f of xi, but then it's because it is in this region, all points in this region evaluated by f of xi will be less than 0. So less than 0 multiplied by +1, it's again a negative number. Okay, so that's why here again it is misclassified. A misclassification is a multiplication of this f of xi times yi less than 0. So we will update your w whenever there is a misclassification. Okay? Any question?
I have a question.
You have a question, Mr. Gopal?
Yes, it says where w is equals to, and then w tilde, comma w naught, and xi is equals to xi tilde, comma 1. What's that 1?
1. Yeah, it's a 1. It is a bias. This is the bias. Remember that in this case here, okay, is this I need a space to write. Because when you okay, let us do here. That's a good question. Well, the 1 corresponds to this one. We want, this is another way, this is just another way of writing that equation. So we write that equation as f of xi equal to w e xi plus b. So in this case, we are saying we tilde it if it's just a two, this one, there are two-dimensional only. So we tilde that one. We also tilde this one. Okay. So that means that in the case of a tilde, so it will be W1, W2 multiplied by X1, X2 plus B. Yeah. So now the final answer will be W1, X1 plus W2, X2 plus B. Okay. But because we want to combine them into this more compact expression, so now instead of the tilde, so we write your f of xi. Are you seeing my screen? Are you seeing what I'm writing? Can you see it?
Yes, sir.
But I can just see half of it.
You can see it. Okay, let me erase the rest of. Let me erase here. I think this is already understood, this part. Okay, this one, we are done. Okay, I'll write here. I'll go here. Okay, so we are saying that we have f of x, okay, I. We want to achieve this expression w1 x1 plus w2 x2 plus b. Okay, that one we understand. Yeah, it is just that expression. Okay, so now we want to make it compact, more compact, so that we will include w0. So now if you have w0 there, so w1, w2, and then w0, you multiply it with x. So now you have x1, x2, and so you must have 1 at the end. So that when you multiply, it will be w0. So now when you multiply, it will be w1, x1 plus w2, x2 plus w0. You understand? W0 times 1, where your w0 is your b. You're just multiplying the vector w1 times x1 plus w2 times x2 times plus w0 times 1 there. So we are getting that expression, and this is equivalent. So it's just another way of writing, so that instead of having a b here, which is that expression, because here you're going to write it as w tilde transpose. Okay, so here you're going to write this one as W tilde transpose X tilde I plus B. Okay. But in this case here, in the other expression, all you need to do is multiply it in a more compact form times X I, finish. Okay. But these two expressions are equivalent. They are equivalent. You understand?
Yeah, I get it.
Okay. Any other questions? Okay, let's continue. So tell me, we'll have a break at 12 o'clock. Okay, now let's continue. So we are done with this one. So if there's a misclassification, what we are saying is we will update the value of W until we correct, we keep on correcting W, keep on correcting W until we get all the classifications correct. Okay. So now Yeah, the same thing here. So when you update, so in this case here, before you update, everything is classified correctly. And suddenly, when you update here, there is a misclassification. So you will adjust. You will adjust. Then the next adjustment, your line will be here. But then again, when you run over here, there's again another misclassification. So you keep on changing until probably your final X will be somewhere that iteratively somewhere here like that. Okay, so that now you classified everything here correctly to be greater than 0, and you classified it correctly to be less than 0. Okay, so that's perceptron. So now, in this perceptron example, this is a program that they run in MATLAB, and it was able to find correct classification, a correct line that will classify both the blue X's against the red circles. Okay, but it can be slow, and the separation line can be close to the training data. So as you can see here, the line, they are correctly separated, but that line touches the blue, some blue data, while it never touched any of the red data. Okay, so now, but still, it was able to generalize correctly. Okay, but then we would rather prefer to have a margin, a larger margin for generalization. What's the margin? The margin we're talking about is this margin of separation. How do we deal with this one so that there's a large separation margin, so that that line, the final line of separation, will be somewhere in between? Okay, so that there is a room for a movement, or a room for room for input perturbance of the input parameters. That means it can play around here, the blue X's can play around here, and the red circles can be around here. Okay, there's a room for perturbance in the data. Okay, so let's go. So this is what we discussed yesterday, that, you know, here there are many ways of classification of these two data sets. That means we would like to have, in our case, we want to have a larger margin. This one has a larger margin, where data points can still play around with this larger margin, while here, there's only a margin for the red, but no margin for the blue. Okay, here, no margin for the red and the blue. So it could be likely that for unseen data, it could be easily misclassified. But here, for unseen data, there's a room for it to play. So for the perturbations of the inputs, it could be most likely still able to classify the unforeseen. Now, what support vector machine does is it wants to maximize this region. There's a difference between perceptron approach and support vector machine approach. In support vector machine, it wants to maximize this region so that the classification can be stable. We want to maximize the margin so that it will be stable under perturbations of the input. Okay, so we continue. Now, how do we do that? So here is the picture of a more detailed picture of what's going on, okay, on terms of data points and the function that we are looking at. So always in this case here, we are looking at linearly separable data, and our equation is linear. The function is linear, that is Wt of x, Wt times xi plus b. Okay, this is the function that we are always looking at this time. So well, we combine them together before W and B, but in this case, never mind. Let's look at it separately. Okay, so now we are saying that if the data point of, if the xi is sitting on this line, if you find a data point on this line and you evaluate the function, Okay, f of xi for that particular point, then the value should be equal to 0 for this point xi. Okay, or let's say for example this is x5. Okay, that is very particular. So if you evaluate f of x5, it will be equal to 0. It should be equal to 0. If it is not equal to 0, then that means you don't have the correct W and B. Okay, so you need to find the correct W and B that will correspond to this x5 being equal to 0. Now, when these are the points here that touches the margin, or the point that is closest to the separation line, or we call it hyperplane. Just say line hyperplane if you can see it from the top to bottom, but if you look at it from the top, then it will be a line. So these data points that are closest to the boundary line are called support vectors. Okay, this is a support vector for the blue and the support vector for the red. Why is it called a vector, a support vector? Are these vectors? Are they vectors? Lignazzo. Lignazzo.
Hello.
Chile.
Yes, sir.
Yes. Why are they called a vector? Are we dealing with vectors here? If yes, huh?
I think the support vectors because they try and guide those lines.
The what?
They give direction for those lines. They guide them.
The guide. Okay. Well, I'm not saying about support vectors per se. I'm asking why is it called a vector? Are we dealing with vectors here?
Yes, we are dealing with vectors.
Okay. Why?
Because there is direction.
Like what?
I don't know what to say.
Where is the direction part?
Direction part.
Yes, you're just giving me a description of what a vector is. It's magnitude and direction, yeah. But then where? Where is it? Can you point out where is that? Are we dealing with all vectors here?
I think some are points, some are vectors.
Some are points, some are, you see. Okay, where are the points and where are the vectors?
I think the vectors are those lines. Then the points are those other points on those. The blue dots and the red dots are just points.
Okay. Okay, thank you, Lynette. But unfortunately, we are dealing with all vectors. These points are all vectors. They are not dots. They are not one-dimensional. They are all vectors. Okay, well, okay, for example, this dot here is a vector. It's composed of, for example, if this is data point 6, x6, okay? Then if this is x6, then it has components, okay? x1 and x2, x1 and x2, 6. That's a vector. Okay, sir, we know it's a magnitude and direction. Yes. So where is the magnitude and where is the direction? Well, the other definition, a rough definition of a vector is that it has more than one component. A scalar, only one. Scalar is not one component only. So A is a scalar value, and it is element of one-dimensional element, R to the 1. So in this case here, X is a vector with two components. Two components there. That's a vector. So then, sir, where is it that we understand before from high school? We are saying it's a magnitude and direction. Well, there's magnitude, yes. Where's the magnitude? So what is the magnitude of the X? How do you compute that? We know this, right? X6, for example, what's the magnitude of X6? Well, that is equal to the square root of what? There, that's the magnitude. Where is the direction? Well, it could be also the magnitude of X6 multiplied by itself. Okay, that's why you multiply and then you take the square root. Okay, I mean, it's just the same. This is the same, but you multiply that, I mean, X1, X2. Well, you have to write it out. So X1 and X2, sorry. Multiplied with X1, X2, there. Okay, and you take the square root. That's the magnitude. So where's the direction, sir? When we're saying that X is a vector like this, it has two components, it should have magnitude and direction. I've shown you the magnitude. Where's the direction? Where's the direction? Moses? We're all dealing with all of these vectors. These points are all vectors. That's why we start with X1 and X2. Every point has a component X1 and X2. This is X1 component, and this one is X2 component. Okay, wherever they're located in that plane, it has an X1 component and an X2 component. There. It has X1 and X2. Everything. That's why it's located in that plane. There's always, if it's why we say XY component, but in this case, we don't want to use Y because Y is used as a classification. So X1 and X2 components. We are all dealing with vectors. So where is, then we compute the magnitude already. Where is the direction? Those components give you the direction. When you have component of, for example, in this case, let's say, for example, this is 5, okay? 5, and this one is 1. So 5, 1, that's already the direction. 5, 1, there, that's your vector. That's the direction of this vector. 5, 1. There, this is the origin, and that's the direction. Or no, minus 1, sorry. 5, because you're going down here, you say this is positive and this is positive. There, that's the direction. When you have components, for sure, that's already the direction. It shows where is that point or where is that vector located with respect to the origin. And that's a vector. Depending on the space, in this case is a planar space, then it has two components. With respect to the origin, the direction, that location of that point, the components show us where is that point located with respect to the origin. So you can draw a vector, and that's the direction of that vector from the origin to that point. Okay. Okay, it's 12. Let's pause for now. It seems, where is this? Stop sharing.